Welcome to this session on energy conversion and storage techniques. So today we are going to do a complete comparison of the different types of energy storage which we have been discussing over the last few lectures. So till now we have seen about electrical energy storage, thermal energy storage, electrochemical energy storage, mechanical energy storage, and finally about chemical energy storage. So five different energy systems. Okay, so electrical energy encompasses your capacitor, supercapacitor, electromagnets. Thermal energy is based on your sensible, latent, and thermochemical energy. Electrochemical involves the storage of energy through the use of batteries, such as lead acid battery, lithium, flow, sodium battery, and zinc battery. So we have discussed in detail many different types of batteries. When it comes to your mechanical energy storage, we have been talking about your pumped hydro and compressed air and flywheel energy storage. So thermal energy storage, we saw about and the temporary storage of thermal energy at high or low temperatures, which can reduce the mismatch between your energy supply and demand. So we have three different modes. One is your sensible heat, latent heat, and your thermochemical storage. So what is your sensible heat? Is nothing but you're going to be storing thermal energy by without changing the phase in which the storage material is in. For example, the increase in the temperature of your water. So by giving heat to your water, you can increase the temperature of your water, let's say from room temperature 23 degrees Celsius up to 60 or 70. So the energy which is there in your water is through the Hensel heat transfer. So it depends on your specific heat capacity of the uh, object of the fluid. So when energy is absorbed, the temperature of within the material rises, and when energy is withdrawn, the temperature drops. So one advantage of the system is it is expected to be completely reversible for a unlimited number of cycles over the complete lifespan of the system. So materials which can be used include solid storage, liquid storage. When you're talking about temperature beyond 100, 500 degrees Celsius, we can use oils, molten salts, and beyond 500, 600 degrees Celsius, it can include concrete and ceramics as well. Very commonly used fluid for your sensible heat storage is your water, mainly because it's easily available. It has got a high specific heat capacity, and it has the disadvantages are it has got low surface tension and it's a corrosive medium. It leaks easily. So you have two different categories. One is your long-term storage and your short-term storage. So short-term storage involves probably the storing of your energy from your solar energy during the daytime and using it in the nighttime, or hot water energy stored in hot waters through solar heating in the morning and reuse heating in the evening or night. So it's probably within a matter of days or few hours. Long-term storage involves even seasonal variation, seasonal differences. Okay, so where are the applications are concerned? We have space heating. So it's, solar thermal power plants are used, and for thermal storage. So a very well-known application is your molten salt thermal energy storage. So we have around 13 gigawatt hour storage installed today, as on today. So it consists of a concentrated solar plants. So the solar radiations are reflected with the help of reflectors onto a central point where the molten salts are recirculated. So this causes absorption of the solar energy into the molten salt, resulting in its heating. It is used at temperatures around 500 degrees Celsius. So liquids can be moved easily, which facilitates your heat transfer. However, the problem is that these liquids, especially molten salts, can solidify. If solidified, it could cause extensive damage to the system. Corrosion has been a major challenge, especially when you're trying to increase the temperature limit for better efficiency. But with this, corrosion has also increases. So the salts which I use in these cases are carbonate and chloride salt. So from this image, we can see about your sensible and latent heat. So when you talk about your water, a temperature below zero, it is there in the form of ice. Between 0 and 100 degrees Celsius is in the form of water, and beyond 100 degrees Celsius, it changes into steam. So any heating or cooling below 0 degrees Celsius or between 0 and 100 degrees Celsius or above 100 degrees Celsius is termed as sensible heat. They give the heat in terms of sensible heat. The change in phase which occurs at 0 and 100 degrees is called as your latent heat. So the formation of water from ice or the formation of steam from water or vice versa involves latent heat. So when you're going to be talking about latent heat, you have the heat which can be stored in ice or the use of something called as phase change materials. So we have seen about the phase changes. The possible options are solid to gas, solid to liquid, and liquid to gas. However, liquid to solid and solid to liquid are the main phenomena which are being used in our day-to-day applications in phase change. So some of the commonly used phase change materials are salt hydrates, paraffins, fatty acids, non-paraffin organic materials, and eutectic substances. So overall, if we see the categorization, it is organic substances, inorganic substances, and eutectic substances. So organic substances refers to your paraffins, non-paraffins, and fatty acids. Your non-organic corresponds to your salt hydrates, and the last one is your eutectic substances. Under eutectic substances, you have again organic and inorganic substances. The next categorization is your thermochemical energy conversion. So here it's a method of storing or retrieving thermal energy through reversible chemical reaction. For example, your exothermic reaction or an endothermic reaction. So when you have such a reversible reaction, heat can be stored in terms of chemical bonds during your endothermic reaction. Heat can be received back when it is your exothermic reaction. So heat energy can be stored or supplied to it to definite chemical material pairs which break the intermolecular bonding between them and separates them into individual reactive components. The materials can store heat energy this way. So the reversible reaction is given there. The former reaction is endothermic. It involves the supply of heat. The reversible reaction is your exothermic reaction. So you have four categories of materials which are support these thermochemical energy storage: adsorption materials, absorption materials, pure thermochemical materials, and the last one is composite thermochemical materials. So the reaction pairs which are generally used are silica gel water, magnesium sulfate water, lithium bromide water, lithium chloride water, and the last one is sodium hydroxide water systems. Applications. So when you talk about thermal energy storage, it's generally in collaboration with your renewable energy systems, such as especially solar energy or wind energy. Because we saw about your molten salt storage system where purely the energy is from your solar collector. So now comparing your three different types of thermal storage systems, you have your sensible, latent, and chemical. So here you have seen about the energy density, which I talked about in the last session. So it's all in terms of gigajoules per meter cube. So it is a volumetric based. So in chemical TES, the value is relatively high compared to the two. Whereas TES, sensible TES system have got a high long lifetime. Chemical TES depends on the reactants degradation. Advantages: low cost, reliable, and when it comes to latent, again we have a small volume, short distance transport possibility is there. When it comes to TES, it has got much more advantages because high storage density, low heat losses, long storage period, long distance transport possibility, and highly compact energy storage. Disadvantages: in sensible TES, there's a significant heat loss over time, depending on the level of insulation, and large volume is needed. When I talk about a latent TES, it has got low heat conductivity, corrosiveness of the material play a major role, significant heat losses. Again, it depends on your level of insulation. Chemical TES, it has high capital cost, it's technically complex. So all these things have been taken from the reference which is given below. You may refer it for more information. So after this TES system, we have discussed about your mechanical energy storage system, which is one of the oldest system for thermal storage. The main attractive feature was the simplicity of the basic concept. So here the energy is used to um, store energy in the form of motion. So you have your pumped hydro energy storage, compressed air energy storage, flywheel energy storage, gravity energy storage, liquid air energy storage, pumped thermal energy storage, and the last one is high temperature heat and power storage. So we have discussed about the first three: pumped hydro energy, compressed air, and flywheel energy storage. So pumped hydro energy storage is also one of the oldest. So if we see the system, you have a lower reservoir and an upper reservoir, which is connected through two different systems. One is through your generating system, and the other is your pumping system. So when you have energy in excess, or you have energy in surplus, or you have energy at low cost, the fluid or water in general is which is there in a lower reservoir can be pumped by supplying this energy. So you store you pump your energy and it goes to your upper reservoir. Now in times of need of this energy, So the energy is now stored in the upper reservoir in terms of potential energy or pumped hydro energy. So in times of need of this energy, either due to demand or peak, then the water can be allowed to flow through a turbine. So through this, energy can be generated. So we have also talked about the turbine generators. So this turbine rotates and generator converts the mechanical energy of the turbine into electrical energy. Electrical energy is connected to the grid from which the place at which the power is required is met out. So here we involve the use of energy from a wind turbine or a PV array. So these are all seasonal energy producing devices. From this, depending on when we have a high production, we can store the energy from these renewable energy systems. So this, the connections from your upper reservoir to lower reservoir is called as a penstock. So as of now, we have 250 gigawatt peak demand. Global capacity is around 180 gigawatt. So typical power plant varies from 50 to 2100 megawatt. So when you consider systems which are currently in India, we have two systems which are under planning, four systems under planning, and two are under construction. So these are the images of one of the biggest system which is there in Lithuania. So the energy is used in transporting the water from the lower reservoir, which is basically a river, to a upper reservoir. So the pipes which you see in the photo are called penstocks. So here you can see the upper reservoir, which is at a elevated area. So energy is used to pump the water from the lower to upper, and during the times of need, the water is pumped back through the turbine, and it can be used depending on the need. So it's a very simple technology, but what are the advantages and limitations? Advantages: it has got low storage cost per unit energy. It has got an estimated value of $0.01 per kilowatt hour. It has got the lowest compared to even lead acid batteries. So lead acid batteries we have already seen as one of the most reliable and still used because of its economy. What are the limitations of the system? Geographic site location is a limitation because it requires different elevations. The project involves a huge cost, very high construction period, and extensive planning for such a project. The next system under mechanical energy storage was compressed air energy storage. So when energy is there in surplus, your air can be compressed and it can be stored as compressed air. So here it involves the production of heat during the compression cycle. Now when energy is required, again this compressed air can be sent through a generator, turbine generator system and expanded, and this can give out the stored energy. Depending on the heat which is produced, the management of this heat which is produced, we have three systems, which is adiabatic, diabatic, and isothermal system. So these systems are overall again classified as large scale CAES or small scale CAES. So adiabatic system, as the name suggests, you store the heat in phase change materials, for example. So here we see the use of your thermal energy storage in your mechanical energy storage as well. So this stored heat is used to reheat the compressed air before expansion in turbine, making it more efficient than a diabatic CAES system. So overall efficiency is limited by the heat loss during compression and estimated to be in the range of 55 to 65. So also while discussing in our units of conversion, we have talked about the efficiency and why efficiency can become high up to 100% is because of this heat loss. Next system is your diabatic system, where this heat which is generated during compression is directly released to the environment. But when expansion, again you need energy. So there you use a fuel such as natural gas to expand the rate. So where is this compressed air stored? It is stored at salt caverns, hard rock caverns, aquifers, depleted oil and gas fields. Above ground storage, it could be in pressurized vessels. Challenges. One of the key challenges is your structural integrity. When you're going to be storing this compressed air in your underground caverns, the integrity of your below ground installations plays a major role. Since you're going to be dealing with high pressures up to 200 bar pressure, it is very important that your storage is safe to operate. So there are operating constraints as well. The cycling frequency can be restricted based on the structural integrity of the underground formation used. So although this technology has been well developed, still you have a very few large scale systems in the last 30 years. The next system which we discussed was the flywheel energy storage. So energy is stored in forms of a spinning mass. So flywheels are well suited for high power applications due to the ability to absorb and release energy quickly. So here you have your flying mass, which is denoted by that flywheel rotor. So it rotates on this radial bearings and thrust bearings, and it is completely housed in enclosure. So you have this thrust bearings on both ends. So when you have power in excess or when it's not needed, you can use it to run the flywheel at high RPMs. And depending on the times of need, the flywheel rotor can be slowed down and the power can be taken out. So one application is by Schwarzkopf Industries. So these are manufacturers of the roller coaster trains. So roller coasters, as you know, they can accelerate suddenly to very high speeds. So a flywheel which is running at 1044 RPM is used to power the train in the roller coasters by 3 times. So the speed increases by 3 times due to this use of flywheel. So there are two types. One is your low speed and your high speed. Low speed operates at a relatively lower RPM of 6000 RPM. High speed operates at RPMs of 10,000 to 100,000 RPM. So they have a high self-discharge rate of approximately 20% per hour. So they can be used only for limited time. So thus comes the second point, limited storage capacity. And the last point is the safety concern. In case of failure, you are going to be dealing with a large disk at high speed. So the next energy storage after this mechanical energy storage which we discussed was your electrochemical energy storage. Here we discussed about the storage of energy in terms of interconversion of chemical and electrical energy through redox and reduction reactions. So batteries comprises of two electrodes immersed in an electrolyte which can be liquid, paste or solid. The electrolyte facilitates the movement of ions between the electrodes, completing the internal circuit of the battery. So we talked about first lead acid battery. So although they have the lowest energy density by weight and volume, their high performance over cost ratio has made it a popular choice for users. So it consists of lead and lead oxide electrode, which is dipped inside sulfuric acid electrolyte. So this is the reactions. Lead reacts with HSFO minus to form PbSO4 and two electrons. Those two electrons are used in the positive electrode to produce PbSO4. So thereby electron transfer occurs to the external circuit, which constitutes electricity. In both the reactions, you see that PbSO4 is formed by usage of H2SO4. So hence, one of the main disadvantages, it cannot be drained completely. So as mentioned here, they are not allowed to discharge beyond 50% depth of discharge. Special batteries have a ability to discharge up to 80%. Another issue is with the formation of this PbSO4. They are twice as dense, so they have trouble fitting into the space. So as you have already seen, lead acid batteries, they are housed inside a complete plastic structure. So you don't have much space for higher density substances. So they have high heavy weight, low specific energy, high cost. And last one is acid stratification. Due to the consumption of the sulfuric acid, uh, it results in the accumulation of sulfuric acid at the bottom of the cell. So sulfuric acid is heavier than water. So when the battery is not in use, the acid tends to settle down. So now there are advancements in these batteries to enhance the performance and address some limitations. So we discussed about two batteries, lead carbon batteries and bipolar lead acid batteries. So the first one is lead carbon battery. You can increase the density, cycle life, charging discharge capabilities. And the addition of this carbon enhances the electrochemical activity of the negative electrode, thus reducing sulfation, which is the crystallization of lead sulfate. So globally, we have around 27.4 megawatt installations using lead carbon batteries. Then we saw about your bipolar lead acid batteries. So we involve the use of recyclable materials and they have a higher specific energy and energy density. Coming to lithium batteries, the positive electrode is a lithium transition metal oxide, negative electrode is a graphite based material. So depending on the lithium transition metal, the name comes. We have LCO batteries, LMO, LFP, NMC, LTO, and NCA batteries. So each of these batteries play a major role, and if all these batteries have come with technological improvements. So we will directly go to the comparison of these batteries, which we discussed earlier. So energy density, the lowest is given by LTO batteries, 50 to 80 watt hour per kg. Highest is by NCA batteries, which is 4 times more, 200 to 260 watt hour per kg. The other batteries vary between 100 and 200. Cycle life is the highest for the LTO battery, which has got the energy density, lowest energy density of 5,000 to 15,000 charge cycles. However, the battery NCA, which had the highest energy density, exhibits the lowest cycle life. Safety is best in class for LTO batteries and lowest in terms of NCA and LCO. Cost is very high for NCA and high for LTO. The other batteries are reasonably okay. Thermal stability, very high for LTO and lowest for NCA. So when you compare all these batteries, we have a compromise. The batteries with the lowest energy density have got the highest charge life and the best safety and very good power output, very high, very good thermal stability, extremely fast charging. Whereas exact opposite is there for other batteries like NCA. So depending on the need, the batteries are designed and used for the particular specified applications. Next we saw about flow batteries, which are similar to a normal battery, except that the materials are stored in tanks and they pump to the reactor. For example, we have the vanadium redox flow batteries. Then we saw about sodium batteries. So this is an improvement in terms of your materials used. Instead of lithium, we can use sodium due to the low cost and widespread availability. Then we move on to your electrical energy storage. So we had your electromagnetic energy storage and electrostatic energy storage. Certain literatures do categorize electrochemical and hydrogen under EES. So where are these electric energy storage devices used? In your household applications, especially your washing machines and your fans where you see these small devices. So these devices store the energy temporarily and give the sudden burst of energy required for starting up your motors. So you can see in the plot, initially between 0 and 5 seconds, your energy required by your motor is around 25 to 30, whereas your normal running condition requires around 6. So this is provided by these capacitors. Now advanced capacitor is what a supercapacitor is called. So we talked about the advantages of a supercapacitor. So a normal capacitor will have a capacitance of around 100 microfarad, whereas a supercapacitor can have up to 1 farad as well. Then we talked about your superconducting magnetic energy storage. So where the entire system is cooled to cryogenic conditions. So when it's cooled to cryogenic conditions, electrical conductivity is increasing and energy loss is minimized. So the wire which is made up of a superconducting material that has been cryogenically cooled below its critical temperature. As a result, electric current can pass through the wire with almost no resistance, allowing energy to be stored in a SMES system for a longer period of time. So some of the common materials are mercury, vanadium, niobium, titanium. And these SMEs are considered far expensive than other energy storage technologies like lithium ion batteries. However, these play a major role in applications such as your manufacturing of your chips, microchip fabrication facilities. Disadvantages are high cost, cryogenic temperature, material fatigue due to the strong magnetic field. Okay. So with this, we come to a end of your first unit. So these are the textbook and references which are there in your syllabus. We have used those same materials for preparation of the materials in these lectures. The last two materials are available online. It is from your Smart India Smart Grid Forum and your MIT Energy Initiative series, where we have taken the materials for this presentation. We hope you enjoy this first unit. Looking forward to seeing you in the second unit. Thank you.